Okay.
Hello, Neuro Insights listeners. I'm Ritika Datta, and we are closing our series with emerging biomarkers for early detection across neurodegenerative disorders, revolutionizing diagnosis and information, and several interventions. Our guest, Kanak Chaudhary, with her master's in biotech, excels in biomarker discovery. Kanak, thanks for being here in the show. To start, could you give us an overview about liquid biopsies, which includes analyzing CSF, blood, or exosomes, capture neurodegeneration signatures like neurofilament light chain before clinical symptoms really arrive to the scene?
Yeah, sure, I'll tell you. Thank you so much for having me again. So, the liquid biopsies have transformed our ability to detect neurodegeneration at very early stages. The neurofilament light chain, or we can call the NFL, is particularly valuable because it reflects the axonal injury and arises years before overt symptoms in disorders like ALS, Alzheimer's, and Huntington's. The CSF has been the gold standard in this part, but advances in the ultra-sensitive assays now allow the detection in plasma and even exosome-derived fractions. These exosomes carry the neuron-specific proteins and RNAs, providing a more direct window into the CNS pathology without invasive lumbar punctures. And the big advantage is longitudinal tracking. Changes in these biomarkers often precede imaging findings or clinical decline.
That was an indeed broad scope. So let's move into protein bio-based markers. So phosphorylated tau and alpha-synuclein oligomers are key. What ultra-sensitive bioassays like SIMOA, like SIMOA, detect these in peripheral fluids, and how do conformational variants distinguish Alzheimer's from Parkinson's in prodromal stages?
Yeah, those SIMOA or single molecule array technology is a breakthrough in detecting very low concentrations of proteins like p tau and alpha synuclein in blood. For tau protein, the different phosphorylation sites such as p tau 181 and p tau 217 are particularly good at differentiating the Alzheimer's from normal aging. Meanwhile, the misfolded alpha-synuclein oligomers detected through seed amplification assays help pick out prod, uh, the prodromal Parkinson's disease. And the conformational fingerprints of these aggregates matters a lot. In Alzheimer's, tau strains differ the structurally from those in frontotemporal dementia, and similarly, the alpha-synuclein in multiple system atrophy is the distinct thing from Parkinson's. This level of molecular resolution is critical for precision diagnostics.
Right, that was pretty precise. Let's move into neuroimaging synergies. PET ligands for amyloid and tau integrate with MRI for atrophy mapping. How do diffusion tensor imaging DTI metrics correlate with biomarker levels, and what machine learning fusion enhance predictive accuracies for disease trajectories?
The PET ligands like PIB for amyloid and newer traces for tau gives us direct pathology map, while MRI provides the structural and connectivity data. The DTI in particular quantifies white matter integrity and intrinsically it reduces the fractional anisotropy, often tracks with rising NFL or tau levels in blood and CSF. So the machine learning models are now integrating these multimodal data streams, fueled biomarkers, imaging metrics, and cognitive scores to predict not just how we will develop the dementia, but how fast the progression will occur. These predictive fusion outperforms any any single modality, also offering a personalized risk trajectory for patients that are there.
Okay, that was pretty integrated. Let's talk about genetic and epigenetic markers. Polygenic risk scores and miRNA profiles in exosomes are cutting edge. How do these predict conversion from mild cognitive impairment, and what CRISPR validation in organoids confirms their causal role?
The polygenic risk scores aggregate thousands of genetic variants to stratify the risk, and when combined with fluid biomarkers, they sharpen the predictions of who with mild cognitive impairment will convert to Alzheimer's. And on the epigenetic side, the miRNAs packaged in exosomes regulate the synaptic and inflammatory pathways. The central miRNA signatures have been shown to precede the clinical decline also. And what's exciting is the use of CRISPR based things that are there, like CRISPR engineered brain organoids, by editing candidates genes or miRNAs. The researchers can directly test whether altering these regulators changes the amyloid accumulation, tau phosphorylation, or the synaptic health. This bridges the association with causation, something biomarkers have good long needed.
Right, they were very causal insights. Let's move on to inflammatory and metabolic panels. So, cytokine arrays and lipidomics identify neuroinflammation. What multiplex platforms reveal about gut-derived metabolites in blood as proxies for brain pathologies, and how do they inform microbiome-targeted interventions? Really,
The cytokine multiplex panels highlight the systemic inflammation that mirrors the neuroinflammation with the IL-6, TNF alpha, and chemokines consistently elevated in early diseases. And lipidomics adds another layer into it. The alterations in sphingolipids and phosphatidylcholins often parallel the neuronal membrane breakdown. Importantly, the metabolomics shows that gut-derived molecules like short-chain fatty acids, or I can say that tryptophan metabolites, reach the bloodstream and correlate with brain pathology. These findings are fueling microbiome-based interventions that are like probiotics, prebiotics, or dietary strategies tailored to the normalized metabolite profiles and potentially delaying the neurodegenerative cascade.
that was indeed holistic, actually. Let's look into challenges and validation. Biomarker heterogeneity across ethnicities and comorbidities complicates its entire use. What global cohort studies address this, and how do wearable tech for digital biomarkers complement traditional assays in real time monitoring?
The large-scale consortia like ADNI in North America, EPAD in Europe, and the Asian Court initiatives are crucial because the biomarker thresholds can vary by ethnicity, sex, and even comorbid conditions like diabetes. Without diverse cohorts, the diagnostic tools risk being biased. The complementing these can be the digital biomarkers from like we can say the wearables like tracking gaits, speech, or sleep provide continuous real world data that fluid assays that cannot capture the real thing. But the integrating molecular biomarkers with these digital signatures offers a fuller picture of disease onset and progression in diverse populations that are there.
Right, so AI-driven biomarker discovery from big data is extremely transformative. How might federated learning protect privacy while accelerating validation? And what ethical frameworks ensure equitable biomarker access in global neurodegeneration research?
So the AI is revolutionizing biomarker discovery by mining vast multiomics approach and imaging datasets for hidden patterns. The federated learning allows the algorithms to be trained across hospitals globally without raw patient data leaving the local servers, and which preserves the privacy while expanding the sample diversity. On the ethical side, the equitable access is vital. Without deliberate frameworks, these advanced diagnostics may remain confined to the high income countries, and policies ensuring the affordability, infrastructure support, and the inclusive trial uh, participation while determine whether the biomarker based precision medicine truly reaches the patients worldwide.
Right. Thank you, Kanak, for enlightening us on biomarkers. That wraps up our series. Thank you, everyone.